Okay, today we're going to begin a very important topic called quantification. Here's some homeworks back from last time. And before we get to the actual topic, I just want to make one more comment, or two more comments before we about types. Okay, so you know when we do textual substitution, the way textual substitution works is this. Suppose you have expression E and you want to do textual substitution, X replaced by F. The thing about the types here is that any time you have a variable is replaced by an expression, the types of X and F have to match. They have to be the same. Remember we said that a variable can have a type, but also an expression can have a type? So whenever you do textual substitution, with this textual substitution, X and F must have the same type. So in this, X and F must have the same type. Now the reason we never did have to worry about this up until now is because up until now all of the textual substitutions and all of the expressions that we did, they were all Boolean expressions and all the variables were Boolean variables.
Sure.
Okay? But if now we're getting to an area where all the variables are not necessarily going to be Booleans. So we have to be very careful what the types are. And in fact, keeping track of what the types are is going to be the key to not making mistakes when we get into quantification. Okay, so that's the first thing. Now, the second thing, that's fact number one. Second fact is, suppose you have an equals in B equals C. Now, we all know what equals means, right? Now, what's the difference between equals and equivalence? Which one works just for Booleans? Which one is just... Equivalence is just for Booleans, but equals is for what?
Anything.
Yeah, for Booleans. It also works for numbers, but actually it works for any type, right? Remember we had all those types up on the board the other day, or up on the screen the other day? So, I mean, you could have some real number equals another real number. You could have some Boolean equals another Boolean. You could have some integer equals another integer. Okay, so, but the point of it is that whenever you use equals, what do you suppose has to be true about the types of B and the type of C? They have to be the same. Okay. In this, B and C must have the same type. Okay, so now here comes a review question from yesterday that everybody always forgets. If you consider equals to be a function, what is the type of the function? If you consider equals to be a function, if you consider equals to be a function, and the types of B and C, okay, and the types of B and C to be T. So this little t could either be, either t could be an integer.
T, arrow, Boolean.
Oh, very good. If you consider equals to be a function and the types of B and C to be T, the type of the function is...
People forget that.
The type of the function is T cross T arrow Boolean.
I have a question about the first thing you said.
Mm-hmm.
Where you have E with X replaced by the entire expression F.
Right.
How can a variable and an expression have the same type?
Yes.
An expression has like T cross T arrow.
Well, whatever this expression is,
Same type.
it has some type. If this expression is going to be, suppose this expression is A is less than B, where A and B are half-type integer.
Okay.
Well, but then A is less than B is type Boolean. So if you're going to have X replaced by A less than B, then X had better be type Boolean.
Okay, so whatever it returns is the...
Whatever it returns, yes.
Okay.
Yes. Whatever it returns, that's the type. Those are the types that have to match. Okay? Is everybody clear on that? And the reason you can think of this as T cross B arrow B is you can think of this as like equals, here, equals BC. So this is the function that returns type Boolean, but each one of these has to be the same type. So if they're type T, it's T cross T. So this could either be R cross R arrow B, it could be Z cross Z arrow B, you know. It could be B cross B arrow B. Because, you know, if yeah, to see if two equal, yeah.
Can you have multiple?
Yeah, functions can have multiple arguments. Functions can have, you could have like 3 or 4 arguments.
Can you have multiple
Yeah, and
types?
then which Boolean?
Oh yeah, each individual, yeah, that's quite common, is to have different types for the individual arguments. That's quite.
Equals?
Oh no, sorry, not for equals, for functions in general.
Oh, for
For equals there has to be 2 because equals is a binary infix operator.
3. You can't
Well, no.
equals.
Well, all right. Now, so what if there are 3? So what if you say A equals B equals C? Remember, what's the meaning for equals? What's the meaning of this?
B, A equals C, B equals C, B equals A, C equals A.
No way. What is the conjunctive meaning of this? You said way too much. What is the conjunctive meaning of this?
They all equal each other.
I know, but you're saying too much. What is the conjunctive meaning of this?
Transitivity.
True.
No.
True.
No. What is the conjunctive meaning of A equals B equals C? What is the conjunctive meaning? What is the conjunctive meaning of this?
A equals B and B equals C.
Yes, the conjunctive meaning is A equals B and B equals C. So basically equals is still a binary infix operator.
Right.
Okay, and this is an abbreviation for this binary infix operator between A and B,
So the
and this
equals-
binary infix operator between B and
This
C.
function only has 2 parameters.
The equals function only has 2 parameters.
Got it.
Yeah, in answer to your question, can equals have more? Well, no, it only has 2 because it's binary infix. But this is what this means. Yep. Are we good? Okay, you guys. Now starts a big topic. Everything that we have done up until now has been, what calculus have we been talking about? Propositional calculus. And what is a proposition?
Something that can either be
A what?
Something that can be true or false.
No, wait, something, be more
statement.
specific. It is a proposition is a statement that can either be true or false.
Siblings.
Okay? It's a statement, for example, you know, this desk is red. That's a statement that is either true or false. It happens to be false, but it's a statement that can either be true or false, right?
Yeah.
Okay. Now, and so the calculus that we have learned so far is called propositional calculus because each one of those P's and Q's and all those implies and all that stuff, each one of those P's and Q's, those can represent statements, variables that could represent statements that are either true or false. And then the question is, if you have P and Q, when is that true, when is that false? And then we developed all this, you know, scores of theorems, you know, starting with some axioms. We did all of that stuff. Now starts another whole new kind of calculus. What we're doing now is not called propositional calculus, it's called predicate calculus. Okay? And the operation that is the central to predicate calculus is this process called quantification.
I'm learning way more calculus than this.
Now here's how quantification works. You have actually seen this before, I'm sure, in your math classes. Because here is what it is. Now tell me, have you seen something like this before? Sigma I equals 1, 3 I squared.
No.
Now you have seen this before, I'm sure, right?
Yes.
I hate it. It's gross.
Yeah, well,
We're not-
we're going to do it better. If you hate it now, if you hated it then, you'll love it now.
Really?
Yeah, we're going to do it better. Okay, now watch this. So so here we have this big sigma, we have this I equals 1 down here, we have this big 3 up here, we have this I squared. So do you guys know what this means? I mean, do you guys know what this means, right? The sigma means add.
Squared is I goes from 1 to 3.
So if you were to write it out, what would it be?
1 squared plus 2
2
squared plus 3 squared.
1 squared plus 2 squared plus 3 squared. Okay? Now, does everybody understand this? Right, you've seen this before and you understand it. Okay? Now, this is a very simple, this is an example of a quantification. But, now, your math professors aren't going to like this because we're going to do it a different way. We're going to use a different notation in formal methods. And I'm here to tell you that our way is better. But unfortunately, it's new and people resist change. And so, but, we're going to go with what's better. So we're going to use a new linear notation. We are going to use a new linear notation. So instead of writing it like this, we're going to write it like this. Now what I mean by linear is, you have something down here, you got something up here, you got, we're going to write it all in a line, okay? So here's what we're going to do. First of all, we're going to start with the parentheses, okay? And this operation that goes in between these terms here, this plus operation, we're going to put that plus right here. So we're going to do parentheses plus, all right? And then this little I here, we're going to say plus I, right? And then we're going to have a vertical bar here, all right? And then in this vertical bar, we're going to write down a Boolean expression for which I is true in each one of these operations. And the Boolean expression that's going to correspond to this one is, well, actually, this was 3. Is going to be like this. 1 less than or equal to I less than or equal to, well, okay, we'll go ahead and do 3. 1 less than or equal to I less than or equal to 3. Are you with me?
So it starts at 1 and goes
Yeah, so this, and we are assuming now that I is an integer, right? Okay, and then, so this vertical bar, and then we'll have a colon here. Okay, and in this colon, that's where we put this I squared. So we're going to say I squared.
Okay, how's this better?
You'll see. It will not become obvious how better it is until we get to some more complicated examples. And once you see some more complicated examples, you'll see that it's very nice. All right, now we have to identify. Now look, you guys. Well, this plus is what goes in between these.
So now we can do it with more than...
We can do it with whatever.
Yeah.
Okay. Now the thing of it is that we have these two parentheses, and basically we have 3 compartments. We have this compartment, and then we have the left compartment, we have the middle compartment, and we have the right compartment. And the left compartment and the middle compartment are separated by this vertical bar, and the middle compartment and the right compartment are separated by this colon. Are you with me? That's the structure of it. Okay, that's the syntax. This is the syntax of our new notation. So what we have to do is we have to identify each one of these compartments. Okay, so we have this, and we have this. Okay, so let's identify each one of these. This I is called the dummy variable. Right, actually, here, let me point to the I. Okay. So this I is the dummy variable. Okay, is everybody clear on that? That's called the dummy variable. Okay, it's also, there's a couple of names for it. It's also called the bound variable. B-O-U-N-D, the bound variable. It's also called the quantified variable.
Is it ever called I?
Yeah, sure, it's called I. The quantified variable. Well, it's not always I. You can use whatever letter. You know.
Yeah.
But whatever letter you use, it's the dummy variable or the bound variable or the quantified variable.
Or
No, that's it. It's only got 3 names. Okay, so it's the dummy variable, the bound variable, or the quantified variable. That's what it's called. Now, this part right here in the middle compartment that goes after the vertical bar and before the colon, this is called the range.
That's straightforward.
It's called the range of the quantification. The range of the quantification. And tell me, you guys, the range always has a specific type. Now, I can have lots of different types, but the range always has a specific type. And can you tell what it is?
natural numbers.
1 is less than or equal to I is less than or equal to 3. By the way, what's the conjunctive meaning of this? 1 is less than or equal to I. What's the conjunctive meaning? We just and I is less than or equal to 3, right? That's the conjunctive meaning. But what kind of an expression is 1 is less than or equal to I and I is less than or equal to 3? What is that? What is its type?
Boolean.
It's Boolean. I might be integer, but the expression 1 is less than or equal to I and I is less than or equal to 3 is a Boolean expression. The range is always a Boolean expression, okay? A Boolean expression. Are you with me? That's a Boolean expression. And then this I, or this compartment where we have I squared, this is called the body of the quantification. This is the body of the quantification. Okay, so what do we have? So what are these 3 things called?
What's the operator?
It's the dump. Well, yeah, that's the operator.
Well, the operator.
Yeah, that's just the operator. Yeah. Okay. Okay. So what are the 3? Dummy, range, and body. So that's how we will refer to them. We'll say range this, body this. Okay, that's how we identify them. Okay. So does everybody understand what the syntax of this is like? Okay. Now, what we'll do now is let's do a few more examples and then we'll generalize. Okay. So here's some examples.
Generalization is only good in
Okay, so here, so Ben, here's your problem. You can go first. Plus I, range 1 less than or equal to I, less than or equal to 7, and even dot I, body I. Can you tell us if we were to write it out expand it out like this,
Yeah.
what would that be?
Do you want me to put it in the old notation?
No. We're done. We're not going to use the old notation anymore. That's just to show you that it's similar to what you've done before.
What's even dot I? Does that mean that
Even dot, yeah, think about what even dot I. Well, even dot I returns true if I is even, and it returns, it's a Boolean. It returns true if I is even, and returns false.
the range of the quantification, and that has to be
This whole, it's every possible value for I for which the range is true.
okay. So 2 plus 4 plus 6.
Yes. Does everybody see that? Everybody see how I did that? So this is 2 plus 4 plus 6.
How do you decide whether it's like you're using natural numbers or real?
Yeah, well, remember how if it's unclear, then you can always annotate what the type is. See, so here, another way to write this would be plus I natural number. You see what I'm saying? So you can annotate it right here. So this to make if you want to make it perfectly clear, and then it would be 1 less than or equal to I less than or equal to 7 and even dot I
We're gonna see
body I.
natural number.
Well, I mean, most of the ones that we will deal with will be natural numbers, but you can usually tell from the context, you know.
Can you use the type as a partial range? Like if you said natural numbers, you want to go from 0 to 7, if you just say I less than equal to 7. Because since it always goes from...
Oh, yeah. Well, actually, this could be, here, let me change this. This could be integers, right?
Right.
And this would still, and this is still this. But if you wanted, what you could do, actually, that's a good point. What you could do is you could say, quantification over addition, and assuming that these i's were what? Were natural numbers. Then we know that the natural numbers are, oh, wait a minute, how about, or z plus, yeah. We could do z plus, the positives, and then we could say what? I is less than or equal to 7 and even dot I, body I, and that would still be 2 plus 4 plus 6. Yeah, so you could do that.
Is Z plus included in 0?
No, z plus does not include 0. Check on that chart. Yeah.
All numbers.
Okay. All right. So, Kyle, how about this? Plus I, range 1 less than or equal to I less than or equal to 7 and odd dot I, body 2 times I. So what would that be?
2 plus 6 plus 10. Plus
Well, don't multiply them out. Let's keep this form.
2 times 1 plus 2 times 3 plus 2 times 5 plus 2 times 7.
Plus 2 times 3 plus 2 times 5 plus 2 times 7.
Can you simplify it in the beginning and just write 2 parentheses and then 1?
Oh, but that's the kind of stuff that we will see how that will be in our theorems and axioms.
Okay.
All right, and of course, right now we're not interested in actually what this additions and what we're just interested in the form because we're gonna okay. All right, Mason, you get this. The dummy can actually be a list of variables. So what do you think this is? Suppose we have plus I comma j, okay? Range 1 less than or equal to I less than or equal to 2 and 3 less than or equal to j 3 less than or equal to j less than or equal to 4 body I to the j. So because this can be a list of variables and this so what do you think? Can you think of what that would be if you were to expand it out? It's I to the j. Well, look. Okay. All right. Okay. Mason. Tell me. What are the possible values of I? What are the possible values of j? 3. So what are the possible values of I to the j?
Would it be like 1, 3, 1, 4?
To the
1 to the 3.
1 to the 1 to the 3.
And 1 to the 4.
But what do you mean and? Plus.
Yeah.
Because this plus is this plus, right?
Yeah.
Okay. Plus what?
1 to the 4.
plus 1 to the 4,
and 2
not and,
plus
plus
conjunction 2 to the third
2 to the third
plus 2 to the
plus 2 to the 4. Okay, now does everybody see how that works? If you have a list of ones, then it's all the possible.
That sucks.
No, it doesn't. That's
Well, if you have like 3 variables,
well,
it's
yeah,
not like a range of 2 values.
yeah. Well, I mean, you know that it is what it is. I mean, you do how you do it. Okay, you do it how you do it. All right. Now, here's the thing. We did this with plus, but you can do it with lots of different operators. Well, but not every single operator. There is a certain restriction on which operators you can do quantification with. And here is the restriction. The operator must be a, drum roll, abelian monoid. This is what it means to be an abelian monoid. These are the 3 properties that if an operator has these 3 properties, and by the way, what kind of an operator is this? Does it look like with this star thing? What kind of an operator are we talking about? Binary infix. Are you with me? We're talking about a binary infix. Because look, as we expand these out, you know, it's this operated on with this. So one's on the left, one's on the right. So this is in between, right? So it's a binary infix operator, and what are the 3 properties that it has to have?
Symmetry.
It has to be symmetry. In other words, B star C has to equal C star B. Are you with me? It has to be associative.
Equal precedent.
So if you do B star C first and then star that with D, it's got to be the same as doing C star D first and then doing B star that. Yeah? And then it has to have an identity. And what does it mean to have an identity? It means U star B is B, and also B star U has to equal B. Right?
I get it.
Now,
Plus and multiplication.
yeah, so addition does this because, you know, A plus B is B plus A. B plus C is C plus B. And addition is associated. And what's the identity for addition?
Zero.
0.
So we can't do it with subtraction or division.
That's correct. We can't do it with subtraction or division. Ooh, that's a good observation.
Wait, what?
They're not
We-
symmetrical.
Yeah, they're not symmetric. A minus B is not the same as B minus A. So you can't quantify subtraction. What about and?
Yes.
Is B and C the same as C and B? Is conjunction?
Yes.
Yeah.
It is. Are you with me?
Is and the
And is and associative? Does A and B parentheses and C the same as A and parentheses B and C? Yeah. And does it have an identity? What's the identity for and?
True.
Was it true or false?
True.
True.
It's true.
Yeah.
False is the 0.
Yeah.
Yeah. Okay.
He was testing us.
He just wanted to see if the rest of us knew. Okay, does everybody see it? And the point of it being abelian is you can quantify an abelian monoid. An abelian monoid, that's what's legal to put in here. Actually, the word abelian comes from a mathematician. His name was Abel. And as it turns out, abelian, it's a monoid. Here. Since you asked,
Sounds like an alien name.
it sounds like.
I am an alien.
I am an abelian monoid. Take me to your abelian monoid. No, actually, if it's a monoid, just a plain monoid is associative. Associative and has identity.
But if it's abelian, then it's symmetrical.
Yeah. So abelian was the one who investigated the symmetry, what the operations you could do with operations if they were symmetric. Yeah. It's also in in a math class, symmetry is called commutative. That's called the commutative law. So they would say abelian is a commutative operator. Okay? Is everybody clear on how that works? Okay, so the next thing we have to learn are some properties of quantification. All right? Okay. So here are the properties that we're going to look at. Now here we have a quantification, which is, now you understand now that we're doing star x. So now what is star? It's an abelian monoid, and it could be any abelian monoid. So this works for either plus or times or and or. Are you with me? So the star is in general. Okay, it's a general binary infix operator. And here we're just as an example, we're going to have star x, and what is this colon T1?
Of type 1.
That's type 1. So we're annotating the type. Are you with me? So star x of type T1 and comma y of type T2, right? So we're having, this is like this two, these are these two things where each one of these, this could be like colon z and this could be colon z, you know, okay? All right. And then this R stands for, what part is that? What little compartment is that?
Range.
That's the range. And P is the what?
The body.
The body. Okay, so range R, body P. Are you with me? And here's the way it works. Okay. So this, and this we already drew this up, so some of this is review from what we've already seen. Variables x and y are distinct. They are called the bound variables or the dummies of the quantification. There may be one or more dummies. All right, we good for that? We just did some examples here with two, right?
Good.
All right, so here we're defining what bound variables are. Yeah. Okay, next. If T1 and T2 are the types of dummies x and y. If T1 and T2 are the same type, then they might abbreviate the type, only having the type be after one of them, but that means it applies to both of them. Okay, that's, in the interest of brevity, we usually omit the type when it is obvious from the context, and that's what we did over here. Okay, we omitted it for brevity. Is everybody clear? Or is obvious? Okay.
We didn't have context over there.
Well, yeah, we did because you're adding things. I mean, you know, we knew that they weren't Booleans, right?
Oh, sure.
Okay. Now, what about the range R? What did we say the range R always was? It was always a what?
A Boolean.
A Boolean expression. So R, a Boolean expression, is the range of the quantification. Values assumed by x and y satisfy R. R may refer to dummies x and y. So here, does everybody see over here? This range has an I in it. This I is this dummy I, right? Is everybody good with that? Okay, so R may refer to dummies x and y. If the range is omitted, now here's another abbreviation. If the range is omitted, as in parentheses, star x, range, nothing, body P, then the range is true. Okay? So anytime you write this, here, if we do star x range true, or here, if we do star x range empty, or nothing here, body P, this means, it means what? Star x range true P.
Yeah, well,
Now what does that mean? That means that you have, what if you had, here, what if we,
for everything as a
what, yeah, what if we had plus I of type, let's do it like this. So here, if we were to say plus I type, let's say type z plus, body this, I squared. What would this mean? What would this be? If we were to expand it out, what would it be?
All numbers above
What would this equal?
True and true.
No, what would this equal?
It'd be 1 squared.
It would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way up to infinity squared. That's what it would mean. Are you with me? It would be for all the types. It would be for all, because what is a type? What's a type?
A set of.
It's a collection of values, right? So this is the collection of values for all the values according to the type.
If it's reals,
Oh, if it was reals, it'd be like 1.0, all the rationals, all there is, sum of all of them. Yeah, that would be huge.
what would be a sum of reals?
Well, I mean, it's super infinity. Yeah.
It's infinite,
Okay.
No matter what you put in the range.
And now, check this out. P, an expression, is called the body of the quantification. P may refer to dummies x and y. So that's what we had over there, right? P could refer to those dummies x and y. All right? And furthermore, now check this out. This whole thing, here, let me see. This whole thing has a type. Now this is a really important concept, and this is what that doesn't get emphasized in typical math classes. This whole thing has a type. And what is the type of this whole thing? It's the type of what this is. It's not the type of this, it's the type of this. Are you with me? Is everybody clear? So this whole thing has a type. And that's going to be really important. Believe me, there's going to be types floating around all over the place once we get into these quantification and these quantified expressions. And it's going to be very important that you understand, that you keep track of what is a type. And I know it's going to happen. I'm going to say, oh, this can't be right because it's the wrong type. So if you can remember what the type is when we do these manipulations, that'll help keep you from making mistakes. All right. Let me see who is. Okay, Rochelle, it's your turn. What do you think? Plus I 0 less than or equal to I less than 4 colon I times 8. So if you were to write that out, what would it be? 0 times 8. Well, wait. What's in between? 0 times 8, what? Plus what? 1 times 8? Plus 2 times 8? Okay, good. All right, is everybody good with that one?
Yeah.
Okay, Josh, what do you think?
The next one?
Yeah. What's the operator?
The operator is multiplication.
Operator is multiplication. So what do you have? So what would this be?
Maybe parentheses.
Parentheses.
0 plus parentheses 0 plus 1 close parentheses.
Parentheses, 0 plus parentheses, 0 plus 1 close parentheses, times,
Exact same thing.
no, don't say exact same thing. Say it. Tell me what it is. 1 plus parentheses.
1 plus 1.
Close parentheses.
Plus
Times.
etc.
No, do it the last one. Come on. You're so lazy. I've never seen anyone so lazy.
Close parentheses times 3, whatever.
Oh, that's even ends with whatever. I've never seen anyone so lazy. Come on. Okay.
Well, see, we just wasted like this.
Okay, now I'm just teasing. Okay, Ben, what do you think? What's this next one?
0d does not equal 6. And
Wait, say that again. 0 times d
yeah,
does not equal 6,
and
and
1d does not equal 6.
1 times d does not equal 6. Is everybody clear on that? 0 times d does not equal 6, and 1 times d does not equal 6, right? So you take this body, and for everyone, yeah? And the operator is and, yeah? Are we good? Okay. What do you think, Kyle? Now, does everybody understand this b square bracket I?
Nope.
Okay, so b, okay, here. b square bracket I in math, yeah, it's like an array. It's like an array in programming, but in math, it's like B sub I. You know what I mean?
No.
Well, you know, look, have you ever seen this kind of thing before? Have you ever seen this like x, like 3x1 plus 4x sub 2 plus 7x sub 3 equals 10?
No.
Oh, come on. You haven't ever seen that? Seen this?
Never.
This is one variable, this is another variable, that's another variable?
The distance for
I
those,
have-
x1, y1, x2.
Oh.
Yeah, it's just a different variable. I mean, this x1 is a different variable from x2, x sub 2, right? So sometimes we say this, b sub I, because it's like, even if it's written this way, we call this b sub I, because it's like it's like a math variable, b sub I, like this, like a subscript. Okay? Who was next? Oh, so Kyle. So what is this?
Do I have to say the entire thing?
No, you can use ... So what's the first one?
Thank you. B 0 equals.
Zero. B sub 0 equals 0. Then what?
Or
Or
B sub 1
equals 1 equals 0, or ... and then what's the last one?
B sub 20 equals 0.
Yeah. Okay. So does everybody see that that's how those pan out? Right? Are we good? Okay. Now, the next thing we want to see is we're going to start using some symbols.
No, sigma.
Well, actually, we are going to use sigma. Well, I'm not going to dwell on this slide too much because this notation on the left, he's just showing us what some typical math books and the way they do it in other, in math and using the old notation and even the old style logic, in mathematical logic, you have the for all I is enclosed in parentheses sometimes, and it's not clear where the closed parentheses is, and so you don't have to know any of this stuff. But you understand what these on the right hand mean, right? This is the quantification over, this is the plus over I, 1 less than or equal to I, less than or equal to n for the range, body x sub I. So this is x sub 1 plus x sub 2 plus. So this is the way you would write it in some other way. And then, anyway.
They're all like the same, and over there they're all weird.
Exactly. This notation is so much better. This notation is so much better.
Why don't we change?
Yeah, why don't we kill the
Because change is hard. We don't change because change is hard.
We should make
And
them all watch Fiddler on the Roof.
right. On the other
They've
hand,
been doing it this way for hundreds of years.
they've been doing it this way for hundreds of years, and so these computer scientists come on. They come up with it. They take a fresh look at the notation and the system and how to manipulate.
At the same time. We should base what math is based on how much people get paid.
Exactly.
Mathematicians, not that much. People that work at Google, a lot.
Okay, now there is one thing that we are going to do, however, in deference to what is just really, really common. We are going to use these uppercase Greek letters. Well, we're going to use uppercase sigma for quantification over plus.
Why?
We're going to use uppercase pi for quantification over multiply.
Why?
Because in logic, the existential operator, this backwards E, is really, really entrenched. This is so entrenched that the guys who came up with this new system said, well, because we need to talk about existential and universal quantification. Okay, so now here, this is real. The previous slide wasn't all that important. This one is really important. You must know that whenever you quantify over disjunction with or, the symbol for this is this backward uppercase E, what looks like a backward uppercase E. And this E is called the existential operator. Existential operator, okay? And furthermore, when we quantify over conjunction and, the symbol that we're going to use is this upside down A. And this is called the universal operator. Okay? So up until now we've been doing, like over here we did plus. Well, probably from now on we're going to use capital sigma. All right? Occasionally you might drop back and do the actual operator. But we just have to know that when it's in a quantification part of when it's in the dummy part of a quantification, then sigma means addition, pi means multiplication, the existential operator means or, and the universal operator means and.
Is that only in the dummy?
That's only in the dummy. That is only in the dummy. That's only in the, yeah, you never do this. You always do P and Q. You would never do P.
No P.
Yeah, you don't do that.
If I was a superhero, I'd be universal operator, man.
I'd be existential, man.
So is everybody clear on this? Now it's actually interesting because a lot of people don't realize whenever they do, a lot of people whenever they deal with stuff like this, they don't actually realize that it's just quantification over a binary operator in general. They don't realize that a lot of people don't make the connection between universal and conjunction.
It's the same thing.
Well, what I'm saying is we're going to write this as this.
Alright.
Okay?
But what?
Because you get paid more when people don't understand what you're doing.
Now, the last thing before we get on to the actual ones, we have to understand what bound and free means. Bound versus free. Okay? So, here's the definition of free. The occurrence of I in the expression I is free. Okay? So here's what's an expression?
Happy.
What's the definition of an expression?
No, I'm not doing it.
Are you refusing to tell me what either before the parentheses.
Binary.
No, before that, the very first one.
Whatever.
Variable or
Number.
A variable or a
Variable or
constant.
constant.
A variable or constant is an expression. Okay,
Unary, prefix,
binary infix. Okay.
got it.
Okay, so anyway, here, that's a variable, right?
Yes.
Okay, so the occurrence of I in the expression, so this is a free variable. Okay, that's a free variable. Okay, this I by itself is a free variable. Now what's the next part? Suppose an occurrence of I in the expression E is free. So now let's do an expression. Let's do 2 plus I times 6. Now this is an expression, right?
Is I free?
So I is free. Okay? So suppose an occurrence of I in expression E is free. Then if this is free, right, then if it's free in here, it's free in here, right?
What does it mean to be free?
Here, it's free here.
That's Canada, they'll know.
If it's free in this expression, then it's free in this parentheses, right?
What do you mean by free?
Yeah.
Maybe what we should do is contrast it with bound.
Sure.
Okay. Yeah. Okay. One more example, and then we'll call it quits.
So it's either.
Okay. Okay. Check this out. This I is not free because it's bound to this.
Alright. That's easy.
This I is not free because it's bound to
But
this.
that first I is free, isn't it?
No. This I is a dummy variable. This I is a dummy variable.
Alright,
And
well-
every I in here is not free because it's bound. Now on the other hand, look, check it out. If we had a J in here, so suppose we had this. So suppose we had this were I times J. Are you with me? Suppose we had this. J is free. That's what that's saying.
So I is bound now.
Provided that J is not one of these,
Right.
then J is free.
Okay, but I is
But I is bound because this I is this I.
What about the lost I?
Yeah, that's also bound.
Alright, we're all bound. Okay, good.
It's
All right.
because those eyes already have like values that are being told to us, right?
By the quantification. Yeah, yeah.
Emancipate these eyes.
How do you emancipate them? Freedom for, yeah, they're bound. Freedom and liberty, and with liberty and justice for all. And with that, I'll see you on Thursday.
Did I get a
No, we-
43 on this or
Like we
47?
got some southern people that are like, freedom for eyes.
10,
No, freedom
40.
for eyes.